Maybe I'll give it just 1 minute for people to straggle in a little.
Yeah.
All right, are you ready, Miranda?
Yeah.
Okay, then. So welcome everyone once again to the WHCGP. Today we're delighted to have Miranda Cheng, who will tell us about 3D modularity revisited. If you have questions during the talk, just unmute yourself and speak out, or there will be time at the end of the talk, dedicated time for questions. So Miranda, take it away.
Okay. I'd like to first thank the organizers for the invitation to speak here, and it's especially nice to talk about to give this talk here because the title of my talk is 3D modularity revisited. So I'm going to revisit what I talked about in this very same seminar series. I think that was in 2021 or 2020 or something. So I mean, so that's especially nice to revisit the same topic here. I actually borrowed some slides I used for the same colloquium last time around. So anyway, so let me see if I can move. Okay, so some general background, what we're doing, just as motivation, which we won't mention again after this motivation slide, is that we're interested in the topology in 4 dimensions. And according to the Crane-Frankel categorification proposal from the year 94, and which stems from the idea of a TFT, right? So the question asked is, can we categorify 3-dimensional invariants, okay, so to detect smooth structures in 1 dimension higher? Okay, and in particular, right, famously, the closed 3-manifolds invariants are, include the Witten-Reshtikin-Turaev invariants, which are basically up to normalization, like Chern-Simons partition function. And is it possible to categorify those in the same similar spirit as one categorifies the Jones polynomial? Okay, so that's as part of some general motivation. And there's some nice work in 2016, 2017 with using the idea from M theory. In M theory, we know that M5 brains are described by 3D 2,0 SCFTs. So you imagine like compactifying those on closed 3-manifolds, and then you obtain some 3D theory. So this 3D theory, so the 3D is on the left side, you could put it on, on the space-time with boundary. So you could think about the space-time as cigar times time, or equivalently as, a solid torus. So the boundary is a torus, and then you need to specify the boundary condition that doesn't break a supersymmetry. So if you compute the supersymmetric partition function in this space-time of this theory, then it's called the half index of the 3D theory. So then their proposal is consider this half index with admissible by supersymmetry boundary condition labeled by this B label, then I should get something that's a topological invariant of 3-manifolds. So that's a fantastic proposal. And moreover, in this paper, they also proposed or conjectured the relation to the Witten-Reshtikin-Turaev invariants. So this relation involves 2 steps. So the first step is we need to combine in a certain way. Well, they give So we know the explicit formulas, but I'm just not reproducing them here. But just in terms of big pictures, and the first step, you need to combine different boundary condition labeled by this B in an appropriate way. And the second step, which is crucial, is to take the so-called radial limit. So namely the variable tau for for the half index, we'll call them the z hat invariants. The tau should approach 1 over k. Okay, so where k corresponds to the normalized level of Chern-Simons. Okay, so it's normalized, so there you don't have like plus minus 2 and so on. And so, yeah, that's nice, because if you believe that that's the case, then you left the Chern-Simons invariance, which is a function defined on the integers, to a function, the z hat invariance, which is a function, actually a set of functions. The set is labeled by B, the boundary condition. The set of functions living on the upper half plane. Okay, so there's 2 points of views. By radial limit, I mean that you approach, a rational number from within the upper half plane. So the name radial limit comes from the fact that we're used to think about, like this kind of functions alternatively as Q series. So in the Q variable, where Q equals to e to the 2 pi I tau as usual, then this radial limit, this limit approaching a rational number, is indeed approaching, the boundary of the disk. So that's where the name radial limit comes from. So it's just so that you have the mental picture. Okay, that's nice. But then, we get a prescription in terms of the 3D theory, or rather the compactification of this 6D theory. But how do we actually compute it, right? We know too little about the 3D theory to compute it for generic closed three-manifolds. So in the same paper, they proposed this, I'm just gonna click away. They proposed a mathematical recipe to compute it for an infinite family of three manifolds. So these are the three manifolds that's called the plumbed manifolds, which is determined by the so-called plumbing graph, which is a weighted graph. Okay, so there's some okay, so so which is a weighted graph. Okay, I'm a bit confused by the messages, but that's fine. Okay, so there's a weighted graph. So it's a graph and with a weight. A weight is an integer associated to each node of the graph. Okay, so we could alternatively and equivalently represent the same data using the so-called adjacency matrix. So the off diagonals is what you would expect from an adjacency matrix. So you get one when two nodes are connected and zero otherwise. And on the diagonals, you're just filling the weights of the node, corresponding node. Okay. So, so that's uniquely specify Plumb manifolds, but not quite. It's unique up to the so-called Neuer moves, or the 3D Kirby moves, which consists of such, the composition of these moves that I draw below. So the idea is that from this different kind of plumbing graph, you could obtain the different four manifolds with the same boundary three manifolds. Okay, that's why it gives rise to the same three manifolds. So anyways, so there's some redundancy, discrete and manageable redundancy of the graphs. Okay, so with such a plumbing graph, what do we do? So the prescription in their paper is that first you write down the corresponding theta function. Okay, so theta function with the bilinear form represented by this matrix that's the minus of the inverse of the plumbing matrix. Okay, so it's a totally usual, normal theta function convergent on the upper half plane if, this bilinear form is positive definite as usual. Okay, so if this is the case, and then we just put it as a part of the integrand, and with some dress up factors, that's, so you have like some chemical potential associated with each node, and then you have this kind of a factor that's raised to a factor that's given by the degree. So how many nodes this node is connected to of the given node. And then you do a contour integral, which has the effect of picking out basically this chargeless, chargeless component. So you just pick out the part of the integrand that doesn't depend on these. Okay, pick out the constant term. So that's a completely well-defined and algorithm to compute it. Okay, and they also prove that given when such a definition is applicable, it actually gives you a z-hat topological invariance that's related to the Chern-Simons invariance in the way that I described a few slides earlier. So that's nice. And then there's another paper by Sergei and Cyprian Manolescu. They also give another way to compute it, and this time via knot surgeries. So you consider a complement in S3 of a knot. So you take an S3 and you dig out the complement of a knot, and then you glue back the solid torus after some surgery that's given by P over R. Okay, this rational numbers. And then given that, okay, you could write down a two variable series Fk that's associated to the knot complement. And then with this same Fk invariant, you could, with a different surgery, you have a different way of surgery of putting, of putting out these different components together into the z-hat invariance. So more explicitly, the surgery formula is given by what they call the Laplace transformation, okay, that takes into account this surgery, okay, let's label by P over R. And as you could see, we suffer from the same ambiguity as in the plumbing matrix case, namely you need some sign condition to be met in order for the result to be a well-defined function convergent on the upper half plane, or a nice function within the unit disk, in other words. Okay, but it doesn't matter. It's a constraint, but it already gives you so many z-hat invariants to play with. So that's fantastic. And then in the paper with these wonderful co-authors in 2018, we proposed that, okay, you could observe that these z-hat invariants have some very nice properties. On the one hand, there's this, we conjecture that they're given by some kind of a quantum modular forms in some way, okay? And we will give you specific examples that's proven, okay, in the bed. And on the other hand, it seems that they could be expressed, in terms of characters of some vertex operator algebras. Okay, so it hints at some VOA symmetries of the 3D theory. Yeah, that's very nice that you have vertex algebra associated to a closed three-manifold that's even more structured than you started out hoping for. Okay, so let's explain this a little bit, okay? So the first point is that they're related to some quantum modular form. So what are quantum modular form? At this point, we just say quantum modular form, some generalization of modular form. So they transform some kind of way in SO2Z, okay? Fine. So physically, why do we expect such residual sort of quantum, modular symmetry to appear? Just very naively, right? We have a 3D space-time, and which is a solid torus, and in particular, right, the boundary is a torus. Okay, So if you imagine for a moment that your bulk theory living in the bulk of this solid torus is very trivial, then the whole thing should be modular, right? Because it's a mapping class group of your boundary. However, it's not quite trivial, okay? It has some content, but still the content is not as complicated as to ruin all the modular symmetry. Okay, so that's where you could expect heuristically some kind of a residual hint of modularity. So, okay, coming back to what actually is quantum modular form and how it generalizes the idea of quantum modular form, of usual modular form. So here I'm taking the definition, okay, by Sgroi, which, as he said, is deliberately vague. So this version of the definition says that in spirit, quantum modular form is a function such that its error of modularity, namely you just define a new function for an element of SO2Z gamma, okay, that is given by the original function subtracting the function after the modular transformation. Okay, so if this function h of gamma is for all admissible gamma, okay, always has better analytic property than the function if you started with, then this function is something that you call the quantum modular form. So why does that generalize the idea of a modular form? Because if f is just a modular form, then h of gamma is 0 for all gamma. So 0 has fantastic analytic properties, right? So that's why modular form furnishes an example of the broader definition of quantum modular forms. Okay? So in some kind of Venn diagram simplified way of explaining it, we have the quantum modular form, and then they contain the modular form, as we said before. And then I'm sure most of you have heard about mock modular forms, and it will turn out that mock modular forms also generalizes the idea of usual modular forms and fall under the definition of quantum modular forms. And the same thing, similar thing can be said about false theta function. There are also examples, in the sense that there are also examples of quantum modular forms that we will explain. All right, so to explain that, just a little bit of technical definitions is that of isolated integrals. So consider a usual modular, okay, good old honest classical modular form of some weight, and then we can define its isolated integral as, its integral dressed up by some weight factor. And it comes in two flavors. One is holomorphic, okay, the other is non-holomorphic, and they're related in a quite a simple way, okay? And then, for instance, a famous example of isolated integral is the so-called full theta function. So if you take the usual one-dimensional unary theta series, so which is a weight 3-half modular form, W equals weight 3/2 equals 3/2, and then you plug it into the definition, okay, and be careful about the contour and so on. And the result up to some factor will be given by this, infinite Q series, and which is almost a usual theta function. It just has some signs sprinkled in there, okay? That's why they're called full theta functions. All right, so the claim is from this definition of isolated integrals, you could see that they're quantum modular forms. In other words, the h of gamma measuring the failure of modularity is a nice analytic function. Okay, how do you see that? Oh, sorry. How do you see that? If you plug it into this definition and compute the this failure of modularity, and then you use the fact that G is a modular form, and you could show that this becomes a period integral. Okay, so from
Sorry,
some
Miranda, is there
yeah.
some restriction on the weight here?
Sorry?
Is there some restriction on the weight?
On the weight. Well, I have actually some restriction on the form. I want it to be a cusp form.
Okay,
not
that
too
implies
much.
a restriction on the weight, yeah.
Yeah. Yeah. So to be honest, like a half integral weight is a bit tricky, but you can still do it. Yeah, you just have to be careful with the contour. Yeah. Right. So you could write it in terms of like an integral from some rationals to I infinity, and then this tau dependence is completely captured by this weight factor. So you can see that it has nice analytic property in tau. Okay, so after we introduce the actual integrals, we could also take a similar look at the case of Mach modular form. Okay. So famously, a Mach modular form in its modern definition is a holomorphic function, okay, such that you could find this other modular form. Again, usually I'll take it to be a cusp form, and of the dual weight meaning the weight is, sums up to 2, such that if you take this linear combination between this holomorphic function and this non-holomorphic function given by the non-holomorphic actual integral of this other shadow formula, then you get what's called the f hat. We call it the completion oftentimes. And it is not holomorphic, but it transforms like a modular form. Okay, so that's the definition. So how do you see from this definition that the Mach modular form itself has nice quantum modular properties? Well, the way you could see that is from the fact that F transforms nicely. The h of gamma, this measure of lack of modularity of F, is the same as the lack of modularity of the non-holomorphic actual integral. So again, because they cancel, right? The combination is something modular. So again, using the definition of the non-holomorphic Eichler integral, you could write this, h of gamma, this arrow of modularity as some period integral. So that's exactly the same parallel story. Okay, so now back to the first claim in our 18 paper, that z-hat invariants should be some kind of related to some kind of a quantum modular form. So in the simplest example, right, we could prove that for all plumped M3s, so with this kind of plumbing graph, in other words, they're cipher manifolds with 3 singular fibers. Okay, and then they have the right, signature for the plumbing matrix in order for the plumbing definition to be well defined. Then you could show that for each of them, okay, there is a positive integer m such that the z-hat invariance up to some prefactor we don't care about, possibly up to some, like some wrinkles, some finite polynomials, they live in the span of the 4 theta functions of that index. Okay. All right, so and that holds the same same index will do the job for all the spin C structure which labels the admissible boundary condition of this half index. So for all the label B, the same job is done by the same. The job is done by the same level. Okay, so this is something you could prove. Okay, and it's proven. So that's nice. So I would like to pose some questions that in my view was left open from this 2018 paper. And the first of them is, okay, so what we actually see is that these z-hat invariants, they're given by some components of a vector value quantum modular form transforming under SO2Z. But they're not all the components. But I mean, we said that heuristically we expect SO2Z to work, to act. You're not expect to see some subspace of this SO2Z representation. So where are the other components? What are their role in the story? So
Sorry,
that's
Miranda, I don't quite understand what you mean by components. Are you thinking, what is the A? Is the A a spin C structure?
Yeah, so let me go to the next slide to answer. Okay, so I'll go through this example, and if it's still not clear, I'll answer again. Okay, so this example is meant to illustrate what I meant with component. So if you just like take this plumbing graph, throw it into the definition, and then you see this line, okay? You could all see my mouse, I hope. There's 4 terms in terms of the basic components of 4 theta functions of level 42. Okay, and then you could actually combine it to 1. So what am I doing here? Okay. So let me explain this notation because I'll use similar notation, but this not the detail is not important, just to illustrate the idea. So recall that these theta functions, okay, they form a representation of SO2Z or its double cover, its metaplectic cover, if you want. But this representation is reducible when this level M is not a prime number. So we could label, sub-representations in terms of subgroups of its exact divisors. Okay, exact divisors meaning that, yeah. For instance, 42, 6 is an exact divisor of 42 because 6 is co-prime with 7. And 6 times 7 is 42. So that's exact divisor. So for instance, in this case, the sub-representation corresponds to the subgroup, okay, this subgroup with 4 elements. And I could tell you it corresponds to a 3-dimensional irreducible representation. So this 3-dimensional representation has 3 components. And what we're seeing here is 1 component. And moreover, you might think, okay, then I just need to change my spin C structure, aka my admissible boundary condition, and I'll see the other ones. But no, because in this, for this 3 manifolds, there is only 1 boundary condition possible. So you only see 1. Okay, so this is what I'm referring to, this phenomenon that we don't see other components from the story. Okay. So this is the question. I hope it's clear now.
No, so I'm sorry. There's something I still don't understand. You have a subgroup when you write Z hat. You've been writing Z hat sub A and Z hat sub B, and my understanding.
Oh, sorry. That's it. That's the A and B are the same. Like that's
okay. No, that's good. So the A and the B are spin C structures on the 3 manifold. Is that right? Okay. So that's a torsor for what group?
That's a torsion of what group? Yeah, you could. Yeah, you could.
Are they somehow trivialized at infinity or something like that? I mean, what's the
for the plot manifolds we're considering with no loops and so on, it's a finite set.
I see. Okay.
So in this
when you
case,
talk about components, I mean, I could think of that as I could think of a vector whose components are labeled by these spin C structures.
Right. So in this case,
it seems like from what you were just saying, that's not what you meant. You meant components and some.
I mean components or subspace in the SL2Z representation. That's what I meant by component. It doesn't match the component in terms of this B label. For instance, in this specific 3 manifolds, there's only 1 B. The set of the
right. Yeah, you said that. Right. Yeah.
Yeah. Yeah. So okay, you don't see
you're missing some irreducible representations and I see.
This is
Is that right?
This is
okay.
3-dimensional irrep of the metaplectic SO2Z, and we only see 1 directions. So the question is, suppose we believe that SO2Z act. So where are the other ones? So, okay. So after phrasing this question, I can tell you that one of the revisiting is to actually answer this question. But now I'm just, throwing all my questions out. All right. Okay. Is it cool? Can I go on?
Yeah, thank you.
Okay, great. Okay, so here is just say that this phenomenon is not just for that manifold. I'm just writing things out in more details in that case, just to show you what I meant. But I mean, you could show that for all Brice-Korn spheres with three, in this three singular fibers, you could, which is defined in this way. You could always show that you see one component, okay, from a generically irreducible representation and always higher dimensional irreducible representation. So you can ask the very same question, like provably for all these three manifolds. And then it's also observed in all other examples we have seen. That's the first question. Now I want to, phrase the second question, which is a question of reverting the orientation of the three manifolds. Okay, we say that the relation between this z-hat invariance and Chern-Simons invariance is given by the radial limit. That's the first thing we propose, we believe. And the second thing we know for sure is that, in Chern-Simons invariant, if you flip the orientation, you just flip the sign of the normalized level, nothing drastic is going on. But I mean, you get very weird, puzzling conclusion when you combine these two, facts. Namely, that you should flip from tau to minus tau, okay, when you flip the orientation. But in general, I don't know what it means, right? Because we still want to function living on the upper plane. So in this 2018 paper, so what we did was that we look into the theory of modular forms and all that, and we say like, okay, so if I have on one side where the prompt definition is well defined, I compute it, and provably, right? I mean, we've seen the proof that a lot of them, they're just given by full theta functions, namely the Einstein integral of some modular forms. And then I'll say like, okay, it would be reasonable if on the other side, I actually get a Mach modular form, because, according to the theory of Mach modular forms, we know that they behave reasonably, namely, they behave as a way that's consistent with the Chern-Simons expectation, namely flipping u and minus u. Now u approaches some, rational number. When I approach, the roots of unity from within the upper plane. Okay, so we say that these are like, the slogan we use is that when we flip the orientation, and in these examples, the z-hat invariant should be given by like some false and Mach pairs. Okay, so that's what we proposed. And but I mean, that's just completely based on modular form ideas. So let's give an example. Okay, for instance, the example we have just seen, right? It is this three-dimensional irrep example. And then if you look at this function, and if you've been working too much with the Ramanujan's Mach theta function, you will recognize that this is nothing but the Einstein integral of the shadow of the famous Ramanujan's Mach theta function of order 7. Okay, so we have an example of a pair. And very nicely is that Gukov and Manolescu in their paper, using their invented surgery formula, they had a completely different way to compute the z-hat invariance for this flipped orientation manifold, for which the plumbing definition is not available. Okay, But due to its relation with the figure 8 knots, they write it down, and then turn by turn, you could see, lo and behold, it is indeed the same as Ramanujan's Mach theta function of order 7. So that's beautiful. I was very, very happy about that. And then, well, just a side remark, you could ask the same question about the what I call other component, about the SO2Z representations, also on the side of the Mach function, because we know that Ramanujan wrote down 3 order 7 Mach theta functions, and they also naturally form a vector value, Mach module forms, and of 3 dimensions, and again, you only see one of them. But anyways, that's not a question I'm asking. The question is there a more systematic way to obtain these Mach invariants from some calculations, via plumbing graphs or via knot surgeries and whatnot? Because famously, we know that, by specifying the shadow, you don't specify the Mach modular form. It's the map in that direction is not unique. You can always add another modular form and still have the same shadow. So that's a second question, and hopefully we will get to the part where I provide partial answer and at least some analysis. Okay, so if we're cool with the second question, I'll go to the third and last question I'm going to ask. Okay. So the third question concerns the other part of our 2018 paper. We say like these invariants are related to some vertex operator algebras. Okay, and indeed, in the later paper, we did like lots of calculations and generalizing, the calculations not from SU2 to other ADE groups, and we could show in general, like for this kind of graphs, the z-hat invariants are always given by characters of some logarithmic VOAs, as long as the signature of the graphs are such that we can compute things. Okay, so that's nice. But then, the third question is, if on the other side, if we flip the orientation, the answer is given by some Mach invariants. So which VOAs should they correspond to? So that's the third question that I'll answer today. Okay. So yeah, now let's move on to the second part of the talk, where we will, in this paper, I hope to post this week. It's been a long journey. We will revisit these questions and revisit these connections that we proposed just a few years ago. Okay, so where am I? Yeah, here. So let's start. Okay, let's recall the first question. So what are the other components? In other words, where do I see the full SO2Z representations? Okay, so this is a proposal. The proposal is, okay, let's deal with the same kind of manifolds, the plumbing manifolds with the right signature. And then I'm going to introduce generalized what we call the defects invariants. So the change is highlighted in blue. The first thing is that I allow myself to insert, because I'm working with SU2 gauge group in this work just for simplicity. So I'm allowed to insert SO2 characters with the representation of of the highest weight representation with the highest weight given by nu, an integer, times the fundamental weight. Okay, then the character is just this. Okay, and so I associate such representation to the nodes in the plumbing graph that lies at the end node. Okay, so the end of the tentacles, if you want. And then the second thing is that I also change, if you want, the vector in the theta function. Okay, so this is a generalization of, the generalization that has been mentioned in some previous paper. I think the 2017 paper by GPPV, and then this 22 paper that I wrote with Sgroi and Boris Feiging and my student and Sarah Harrison, etc. Okay, so
Miranda, what is this physically? Is this lines or surface defects you're inserting in the partition function?
Right. So we conjecture that they capture the Wilson line operators that correspond to M2 branes wrapping, the links that corresponds to these nodes. Okay. So, but we can't prove that. Just like the original plumbing definition, it's a conjecture. Okay. Yes. So at least mathematically, you could prove that there are topological invariants because you could check that they are invariant under these 3D Kirby moves that I was mentioning earlier. And indeed, as I think that was Greg, right? The conjecture is that they give the answer of the half index when defects operators are included. Okay, so then after that, we moved on to the second formulation of z-hat invariance, namely the surgery formula, okay, for the knot from the knot complement using this two-variable FK series associated to a knot K. And then here we also propose similar, modifications, insertions that's in the blue bubble. And we again conjecture that they're the answer or defects, that's why we call them the defect invariants. Okay, so quickly answer the first question. And the answer is stated in most general terms as a conjecture. Namely, if you include all these defect invariants, then indeed up to some prefactors and potentially finite polynomials, the span of these defects, z-hat invariants without and with defects, are exactly the span of the components of this SO2Z's vector value quantum modular forms. And then you could prove this conjecture for all Brice quantum spheres labeled by 3 co-prime integers that I mentioned before. And then you could also prove similar things using surgery, and not surgeries instead. So, but anyways, just show you explicit example of what I mean. So this is the same manifold we encountered earlier with only one admissible spin C structure. So before inserting the defects, we only see one component. And when you start to insert defects, this vector with 3 integers, they just correspond to like the SO2Z representation you insert at nodes. And then lo and behold, you see that up to some prefactor, you indeed get all the 3 components. So you complete the SO2Z representations. Okay, so that's the answer to the first question. And then so now I move on to the second question, if there's no question on the question or on the answer. So if you think about it, it's very natural, right? I mean, so it just tell you that you really need to include the defects to see the whole structure. And then, yeah, so that's the motivation of that led us to this, exercise, if you want, and then to this proof. So the second question is, how do we obtain the mock invariance? So that is a messy business, I can tell you, as far as I could see. So there are 3 proposals currently. So the first one is what we proposed a few years back, namely to use indefinite theta functions. I'll explain what I mean shortly. And then there's a work by Sung-Yuk Park who says that you could, he basically invented the whole mechanism of what he called the inverted Hopero series, and then he used some very specific kind of analytic continuation using Q hypergeometric series. So very creative. And then there's this recent proposal by these 4 authors. So so I will focus on the first 2 approaches. Okay. So what do I mean by the first approach, by this indefinite theta function? So the idea we had back in 2019 was that, okay, the problem when you flip the sign here is that the signature is not right. So you get like some lattice function of a not positive definite lattice, so they're not well defined on the upper half plane. So this whole thing is just not well defined. You just can't do the contour integral because the integrand is not well defined. So then so let's, to be very specific, let's focus on this kind of plumbing graph. So the simplest one where you could do everything as much as explicitly as much as possible. So we do this so you could integrate all the directions out apart from the central node. The central node is what causes you trouble. Because if you want, because only for the central node you have degree 3, and this dress up weight factor give you something in the denominator and leads you to something infinite. Okay, so you do that, and then you get to indeed this kind of a false theta function of one-dimensional negative definite lattice. So something that's terrible, not well defined. And then don't ask me why at the moment, but the idea we had is like, let's insert 1 by adding a positive definite lattice. Okay, so the numerator and the denominator here are the same. I'm just writing down the definition of the denominator in terms of the numerator. Okay, but in any case, it's a theta function of a positive definite lattice. Okay, let's take this lattice to be one-dimensional, just to see what happens. Okay, so then you get a theta function of a 1,1 lattice, still problematic. Okay, but I mean, this is kind of thing that many of us are familiar with by now, thanks to the work of Schwefers and many other people. He says like there's some natural way to make sense of it. You just restrict the sum to a positive definite cone. Okay, and then you can restrict it by adding a factor in this way. Okay, so you have a cone that's determined by 2 vectors, C1 and C2. Okay, that's orthogonal to it in some sense. And then so you add this factor, which takes the value of 1 or 0 if you're outside or inside a cone. So this is how you restrict the sum to a cone. And once you do that, you can massage it, and it becomes a well-defined function on the upper half plane because you're restricting to a positive definite cone. And then Boost Mach modularity, one can analyze explicitly, again, thanks to Schwefers and many other people. Okay, so let's do that, and let's go back to our favorite example. Okay, so this is our choice of one-dimensional auxiliary lattice that's positive definite. and this is our choice of the cone. And then, you just put the definitions together and you get a Q series in this way. And then it gives you a Mach modular form, which is provably equal to Ramanujan's Mach theta function of order 7. Okay, so this is the way we get and results that's the same as what we expected. Okay, that's nice. And then okay, and then it shouldn't come with a surprise that you could use exactly the same cone for the defect invariants we just defined. And of course, what you get, not surprisingly, is that you get the other components of the Ramanujan's order 7 Mach theta function. So also on the Mach side, if you use this cone structure, you recover all the SO2Z vector value Mach modular form. Okay, so this, if you want, is like just saying like two conjectures are compatible with each other. Okay. And then okay, so in general, we generalize this. I mean, it's quite a tricky computation, so it took some time. But the result is we can generalize this conjecture to other Briscoe spheres when R is 1. That's the example we have just seen with Ramanujan's Mach theta function. Okay, for these, then we could write down the same, generalize the 1D theta function and generalize the cone, okay, in a way that makes sense when we increase R to be other positive integers. Okay, so then you could show that the resulting functions, they have the expected Mach modular properties that's consistent with, if you want, the Mach cos, pair conjecture that we phrased in our 2018 paper. So that's nice. And I want to, next slide. Okay, I want to make a few comments here. So if you want, I mean, it's a little bit, I'm sure you're asking, like, how on earth do I come up with this code? Okay. And so to be honest, to a large extent, we basically reverse engineer, the generalization to other, Briscoe spheres when R is larger than 1 from the Mach modularity that we want to get. And we want a nice looking cone. And then that, preserves the structure of the z-hat invariants on the other side, the structure, of the computation on that side. So there's quite a bit of tweaking and working backwards. Okay, we are not claiming that we have sort of, physical or what other intuition to get this code at the moment. So the second comment, okay, is that so they have this Sawyer Clark had this very highly creative conjecture. It's really fantastic from his paper. And then we realized that if you apply, his conjecture to the torus knots, okay, 2 minus 3 knots, and then using the 1/r surgery for a general R positive number, and then massage it. It looks very different, but if you massage it well enough, okay, and then you actually get to our, answer in terms of cone and so on also. So that's nice. So then we had this idea like, okay, so why don't we just then take his conjecture and apply it to other torus knots? And then again, if you massage it well enough, you could get indefinite theta functions. But it turns out that they're no longer mock modular forms. Okay, so it turns out that in these cases, they're mixed mock modular forms. So what is mixed mock? So it just means that the completion, the thing that is non-holomorphic and transforms like a modular form, is not just, you know, a combination of the original function together with one non-holomorphic Eichel integral of some one modular form. Is a combination of hi, which is some, you know, modular form, multiplying, you know, like the shadow part, if you want. Okay, so then we're like, well, but I mean, okay, so they have different modularity. So does the relation to Chern-Simons still hold? So we show that because you could show some specific properties of this hi, of their behavior near the roots of unities, or near the rationals on top plane. And then you could show that you could still, this still holds, but I mean, now you have more singularity to subtract, not just the singularities from F. Sometimes H will develop singularities near the rational, and you need to subtract those singularities as well. And there again, exponential singularities that we don't know how to interpret it from Chern-Simons' point of view at all. So we just subtract it, and then once you do that, the perturbative part still works perfectly as expected. So that's kind of a surprise for us on the journey. Okay, so that's yeah. So then the fourth comment, if you think like all this is kind of laborious and non-systematic, then we're totally with you. So in fact, we had this idea like, okay, so if you know what Apple-Lurch sums, then otherwise it's just some methods in, you know, the theory of mock modular forms. It is possible to uniformly associate a function as, you know, the reflection, if you want, of all the, you know, basic components of full theta functions for each index and component R. Okay, so once you have, you know, such a uniformly constructed companion on the, you know, if you want, under the reflection, you have all the building blocks, right? So you could write down a proposal for all these z-hat invariants, which cannot be computed in a straightforward way using any definition. And then, moreover, right, you could show that it has the right behavior in order to make sense from a Chern-Simons point of view. Even better, I could give you a vertex algebra with these as characters. Okay, so that seems to be much nicer. But life here is pretty tough. We could show that it gives answers that are incompatible with other points of view. For instance, in that example where there's alternative ways to compute the same z-hat. Okay, it just doesn't work. Okay, so this is too good. So this is, hopefully you appreciate some of the hardship in trying to find the answer on the one side. Okay, so what am I? Oh, I have like 1 minute, 2 minutes left, right? So that's fine. Let's get to the very last question. The last question is, how do we associate mock invariants? Since we make some conjectures for, you know, the z-hat invariants for this families of infinite families of z-hat for these three manifolds. And what about, you know, the other part of the 3D modularity, namely the vertex algebra part? So here we give sort of a simple answer. Okay, so in terms of what we call the cone VOA, so it was written down by John Duncan and Jeff Harvey for one specific, you know, cone. And then my student Gabriele basically generalized it to like arbitrary cone construction. And both papers happen in the context of moonshine, of moonshine. But anyways, coming back to the VOA. Okay, so let's take a lattice of, usually we're familiar with positive definite lattice, but let's let it to have arbitrary signature. And then you know, famously, I'm not going to review here in view of time, but famously you could construct what's called the lattice VOA. Okay, it's a VOA if the lattice is positive definite. But if it's not positive definite, this algebra actually have vertex algebra structure. And now choose a cone with the full dimension, full rank. Okay, that's positive definite. Okay, and you could show that positive definiteness together with this, just the monoidal structure of the cone, is enough to show that you could restrict the lattice vertex algebra to the cone, and that this subalgebra gives you a cone VOA. Okay, and then the modules of them, and also the twisted module, can be constructed in the same way, analogous to the usual construction of lattice VLAs. And moreover, it could show that these characters are given in terms of indefinite theta functions that's characterized as usual by this vector. Okay, in the untwisted case, this vector will be in the discriminant group of the lattice. And using this, we could construct, you know, explicit cone VOAs and explicit modules, such that indeed all the mock invariants we proposed earlier in the answer to question 2 are linear combinations of characters of these cone algebras. Okay, so that's our answer for question 3. Oh my God, no. I'm sharing. I still need to share the last slide. What? I need to share the conclusion slide. Just give me a second. That's no good to press the wrong button. But anyways, you could use that time to think about all the questions you want to ask. Okay, the thank you slide, very important. So that's all I'm going to talk about that I have to say today. And obviously there are many, 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 many generalizations for people to work on. For instance, you could take this to be arbitrary AD group, not just SU2 as we did. And in this generalization, it should be quite straightforward. And I think you will see a lot of fun, like higher depths, mock modular form and all that. And more general cipher manifolds, or even more general plumb manifolds, and so on. There are many things to play with. And then, yeah, so of course, I don't know the meaning. It's a burning question what the meaning is of this indefinite lattice, right? And then also we proposed like VOAs from one side for like some three manifolds and some explicit VOAs on the other side. So the orientation flipped three manifolds. And both sides are very systematic and satisfying, but there should be a direct map between this, you know, like the map of flipping the orientation should have like, you know, a representation as a map of like between two vertex algebras. And as I said, in this other group, they other very nice paper by Girardon, Sgroi, and Costin and Grant. They have this this proposal to the resurgent analysis, and it would be great to, you know, understand the relation. And there are many things one can revisit in the future. And that's all I'm going to say. Thank you very much for your attention.
So thank you very much, Miranda. Let's thank the speaker. And we have time still for a few questions. Oh, I see Greg raised his hand. Yeah, go ahead, Greg.
So, hi, Miranda. So I have a question about these cone VOAs. So another place where we see vertex algebras based on indefinite lattices is, of course, string theory, when the target space is Lorentzian and compactified. So in that case, it's natural to look at algebraic
Sgroi forms,
I'm not. That's not where I'm going. Well, okay, that's another direction. But I was thinking more of, let's take the cohomology of the BRST cohomology, so couple to ghosts, and take the BRST cohomology, and then we know that satisfies interesting algebraic structures.
I see.
Gerstenhaber algebras, operatic structures of various kinds, all that stuff. So, so my question is, are your cone algebras in any way related to the BRST cohomology?
Yeah, now I'm wondering. I haven't thought about it, but now I'm wondering. It's a great question. Yeah. But you know, like from a Q series perspective, the first thing I say, oh yeah, so that's Mach versus Sgroi. But yeah. But,
okay, yeah, that's indeed another
algebraically, I don't know. I haven't thought about it.
I'll just point out that that's what, Borchards does, using them, to talk about the monster.
Yeah, that's right. That's right. Yeah. No, I have not, I have not encountered such a relation. Yeah.
Other questions? Okay, I have a question actually. So, so you were talking in your answer to, I think, the first question, you were talking about how you had some SL2Z multiplets of modular forms, which were first kind of mysterious, and then you understood it in terms of inserting defects in the. So the question is there an a priori way of predicting, if someone gives you if you start with the three-manifold, is there a way of predicting in advance what the SL2Z representation will be, just in terms of how it maps, one defect into another?
Yeah, no, I don't know. I mean, certainly, I mean, back in 2018, we were already like, I was already like banging my head against the wall for this trying. I mean, we know some things. Like, for instance, for Brice-Korn spheres, I can give you the representations. I can give you the SO2Z representations. I could give you which component corresponds to the defect list he had. I can tell you everything. But in general, there are some convoluted formula, like for instance, in the paper I wrote with Gukov, Feigin, my student Davide Passaro, and June and Harrison, in like just indicating like this number m, so the index of the underlying one-dimensional lattice. But there's no way, as far as I could see, to give a closed form formula for which representation.
I see. And do you know if the relation? So you have an invariant. Oh, I guess you don't have an invariant for like the most general configuration of line defects, maybe, but only for some special ones.
Yeah, so we give proposals for the defects corresponding to like knots that are attached or links attached to corresponds to the end node geometrically. Yeah.
Is it meaningful to ask whether the invariant obeys like skein relations?
Yeah, that's another. Yeah, I got quite asked this last week, but I don't know. Yeah. I mean, my guess is no. But my guess is no.
Your guess is that it's meaningful, but it does not obey skein relations.
Yeah, I guess one cannot make that link, but
Okay,
like
okay,
it's
okay.
pretty cool. Yeah.
Other questions? All right. Well, if there are no other questions, then let's thank Miranda again.
Thank you
Thank you,
very
Miranda.
much. Thank you.
And I guess we'll close out this session. So our next WHCGP will be in April, on April 15th, and our speaker will be Brian Williams. And so hope to see you there. All right. And I'll stop the recording.